Welcome to this lesson on nuclear fission, one of the most powerful phenomena in modern physics. Nuclear fission is the process of splitting atoms to release enormous amounts of energy. This discovery has revolutionized our understanding of energy and matter and continues to power millions of homes around the world today. Nuclear fission is the process where a heavy atomic nucleus splits into two or more lighter nuclei when struck by a neutron, releasing enormous energy. This process occurs naturally in heavy elements like uranium-235 and plutonium-239. When the nucleus splits, it releases additional neutrons that can trigger more fissions, creating a chain reaction. Most importantly, this process converts mass directly into energy, following Einstein's famous equation E=mc². The fission process happens in four distinct steps. First, a neutron collides with a heavy nucleus, like uranium-235. Second, the nucleus absorbs this neutron and becomes unstable, beginning to oscillate violently. Third, the nucleus can no longer hold itself together and splits into two lighter fragments, called fission products. Finally, additional neutrons and massive amounts of energy are released. These released neutrons can then go on to split more nuclei, sustaining the reaction. The energy released during fission comes from Einstein's equation, E=mc². The mass defect, which is the difference between the original mass and the final mass of the products, converts directly into energy. Even though the mass lost is incredibly tiny, it releases enormous energy because of the speed of light squared factor in the equation. One single fission event releases approximately 200 mega-electron volts of energy. To put this in perspective, this is millions of times more energy than a chemical reaction like burning coal. Let's look at a specific example. When uranium-235 absorbs a neutron, it splits into barium-141 and krypton-92, releasing 3 neutrons and energy. The fission fragments, barium-141 and krypton-92, are highly radioactive. The 3 neutrons released can trigger additional fissions. Each fission releases approximately 200 mega-electron volts of energy. This example shows how one neutron can lead to multiple fissions through the neutrons it produces. A chain reaction occurs when the neutrons released from one fission trigger additional fissions, creating a self-sustaining reaction. Here's how it works. One initial neutron splits a single uranium-235 nucleus. Each fission releases 2 to 3 new neutrons. These neutrons then cause more fissions exponentially, with each generation producing more and more fissions. This exponential growth is what makes nuclear fission such a powerful source of energy. But it also requires careful control to prevent runaway reactions. Chain reactions can be either controlled or uncontrolled. In controlled reactions, neutron absorption by control rods regulates the process, producing a steady, sustained energy release. This is used in nuclear reactors to produce electricity safely. In contrast, uncontrolled reactions involve exponential neutron multiplication, leading to rapid, explosive energy release. This is what happens in nuclear weapons, with devastating consequences. The key difference is the ability to manage how many neutrons go on to cause additional fissions. The approximately 200 mega-electron volts released per fission is distributed among various forms of energy. The largest portion, about 167 mega-electron volts, appears as kinetic energy of the fission fragments. About 5 mega-electron volts is carried by the released neutrons. Gamma rays account for approximately 7 mega-electron volts of instant radiation. Finally, about 21 mega-electron volts comes from the decay of radioactive fission products over time. This energy is ultimately converted into heat in nuclear reactors, which is then used to generate electricity. Critical mass is the minimum amount of fissile material needed for a sustained chain reaction. If the mass is too small, neutrons escape before causing fission. This is called subcritical, and the reaction dies out. When the mass is just right, exactly 1 neutron per fission causes another fission. This is called critical and maintains a steady reaction. If the mass is too large, multiple neutrons from each fission cause additional fissions, leading to exponential growth. This is called supercritical and can result in an explosive release of energy. Nuclear reactors operate at critical mass to maintain steady power output. Nuclear fission has numerous important applications. In power generation, nuclear reactors produce clean, reliable electricity for millions of people worldwide without greenhouse gas emissions. For propulsion, fission powers submarines and aircraft carriers, allowing them to operate for extended missions without refueling. In medicine, nuclear fission produces radioisotopes used for cancer treatment and medical diagnostics. Finally, research reactors enable groundbreaking studies in physics, materials science, and chemistry. Through these applications, we continue to harness the incredible power of splitting atoms to benefit humanity.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.